Welcome to the sixth section of our Chapter 17 coverage. This section is on standing waves. So a standing wave results from the interference of two waves along the length of a medium. It could be a string, it could be in air. To illustrate that, the first thing we're going to do is watch a couple of YouTube videos together. I'm going to narrate as they happen. So the first one shows you the standing wave on a string, or I think it's actually a spring. And the nice thing about it is it begins by showing you the reflection from a fixed boundary that we saw in the last unit. So you can see it definitely flips to the other side. Now when a standing wave occurs, we can think about the wave on one side, or the incoming wave, interfering with the reflected wave. And if they are in phase properly, so that both of them are at a peak or a trough, then we get a large area of displacement, or if they're opposite, then we get no area of displacement. You could see the NaN notation there. The N is a node. It's a place where the string really isn't moving, and the A is an antinode where the string moves a lot. And every time you move from harmonic to harmonic, then you add one node antinode pair. So here for the second harmonic, we have two antinodes and three nodes. Here is the third harmonic. Now we have three antinodes and four nodes. This, I don't know why he couldn't get the fourth, but he does the fifth harmonic through the eighth harmonic, showing you the nodes and antinodes for each one along the way. Harmonics occur only at particular frequencies for the oscillation. Other frequencies do not support the resonance, and therefore you don't get the same effect. So if we go and look at this YouTube video, we have a young lady who's going to show us harmonics in a tube. This tube is known as a Kunst tube. The sign there behind said that both ends at this point were closed. One end down here has a speaker, and she's going to adjust the frequency. And if you notice, when she hits particular frequencies, then you get the standing wave to occur. Again, a node at either end and an antinode in the middle. And she even tells us the frequency, that it's 119 hertz. Now she's going to adjust the frequency again. Bring it up. And again, two antinodes and three nodes. One on each end and one in the middle. And we notice here that the frequency is now 238 hertz, which is double what we had originally. Turn down the volume here a little bit. Oh, maybe not that far. Sounds like we have some beat frequencies going on there as well, but I'm not sure between what. And the frequency is now 350 hertz, which should be 3 times 119 or down close to it. Now, something happens at this point. I'm not exactly sure what she does, but she changes the boundary conditions so that it is no longer closed at both ends. Now it's open at one end. And you get a slightly different effect. So, and this one she tells you is at 179 hertz, so it's at a different resonant frequency than we've seen before. And that concludes this video. Okay, so let's close that. So looking at this a little bit more closely, we're going to pull in a simulation. Okay. And that simulation is from this website, but you have to download a jar file to get it to work. I have that jar file over here. Maybe. Here we go. There it is. So let's look at fixed ends first. So you can see we have two spots for the most basic oscillation that can occur that don't move. Those would be the nodes. And one spot in the middle where I've roughly marked it with red, where you have maximal movement, and that would be an antinode. Okay, so two nodes, one antinode. As I said before, when you go up in harmonics, you add one node and one antinode. So now we have two antinodes and three nodes. I can go up to the third, where I have three antinodes and four nodes, one node at either end, and one roughly a third of the way across, and then one roughly 2/3 of the way across. And I can keep going. Okay. So this is what it looks like if we have two fixed ends for a string. For a pipe, this would be matched ends. So either both ends are closed, like we saw with the young lady in the video, or it could be two ends that are open, though how exactly that pipe would work, I'm not 100% sure. Okay. Okay. On the other hand, I can look at what happens if I do free up one end of my string. So now you can see I have one node and one antinode, and I get a very different looking oscillation. Okay. Again, I can add one node antinode pair. Right? This end is still free to move, but instead of having one node and one antinode, I now have two nodes, one here and one roughly there, and two antinodes, one here and one roughly here. I can go up again with one node antinode pair. Okay, so again, nodes are places that do not move. Antinodes are places that move maximally. Okay. Now, standing waves can occur when you have matched boundaries, like the string we've seen it fixed at both ends, or pipe that is open at both ends or closed at both ends. Or I could have mismatched boundaries. So this would be a string that is fixed at one end and free to move at the other, or a pipe that's open on one end and closed at the other. We're going to begin by analyzing the matched boundary condition. For the matched boundary condition, what I have is a string. I'm going to fix the length of that string to be L. And then, as we've seen, we're going to end up with a node at either end and an antinode in the middle. So the string actually oscillates between the two dotted lines that I've drawn. Okay. If we focus just at the upper one, we see that we start at equilibrium, go up, and come back down to equilibrium. If I think about a sine wave, for example, I start at equilibrium, I come back down to equilibrium, and if I were to come back up to equilibrium, that'd be a full wavelength, but I only went halfway. So in this case, I can say that the length of the string is 1/2 the wavelength of the oscillation, or in other words, the wavelength is 2 times the length. Now I can use that V equals lambda F. So the frequency is going to be the speed of the wave on the string divided by the wavelength, but we know the wavelength is twice the length of the string, so that would be V over 2L. And because this is the lowest frequency that a standing wave can occur, we call this F1 and call it the fundamental, or you'll also hear it called the first harmonic. Okay. To move to the next one, I add one node antinode pair. So I have one node here, one node there. I need a node now in the middle and antinodes in between. So that would, oh, I'm not drawing this very well, look like an oscillation envelope that looks something like that. Obviously it should be symmetric, but I'm doing my best. So again, following the top one, I start at equilibrium, I go through the equilibrium position and come back. So comparing to my wave, I start at equilibrium, go through it and come back. In this case, the length of the string is equivalent to the wavelength of the oscillation. And if I use the frequency is the speed over the wavelength again, that's V over L. And if I compare this one to that one, we see that this one's twice as big. So I can rewrite this as 2 times F1. And because this is a number 2, I'm going to call this F2. This would be the second harmonic. You may also hear it called the first overtone. Okay. One more. So I need to add one node antinode pair. So if I plot out my nodes, they're going to look something like this. So node, 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 and antinodes in between. I'm going to write them up above a little bit further. So up, down, down again. Stopping here really quick. I'll draw the other half of it in just a second. But if we come back up, I went from here, through there to here. So that's a wavelength and a half. So L equals 3/2 of a wavelength, or the wavelength is 2 over 3L. Again, adding the other side of the oscillation envelope. I can now come over to frequency being speed over wavelength. Putting in my wavelength is 2L over 3, and remembering that the denominator of the denominator flips up to the numerator. That's 3V over 2L. And if I compare this frequency to this one up here, I see that it is a factor of 3 bigger. So this is 3F1. So F3 is 3 times F1. And this would be your third harmonic. Hope I have room. Or your second overtone. Okay, so summarizing what behavior we see for standing waves when we have matched boundaries. The fundamental was given by V over 2L. And all the higher ones I can find by multiplying by the number of the harmonic times the fundamental. So F2 is 2 times F1. F3 is 3 times F1. And that value of n can be any integer. Okay. On the other hand, as we saw for mismatched boundaries, I had a node at one end where it was fixed, and at the other end I had an antinode. So the oscillation envelope looked something like this. If I come back to my wave, that's going from here up to here. I never make it back down to equilibrium. A full wavelength would be here, so I've gone a quarter of the way across. So the length is 1/4 of a wavelength, or in other words, the wavelength is 4 times the length. That's a 4, not a 9. And now I'm going to pull F equals V over lambda again, which is going to be V over 4L. And this, for this set of boundary conditions, is the lowest possible oscillation frequency allowed. So this would be the fundamental in this case. Okay. Now, again, to move upward, I add one node antinode pair. So I have two nodes now. Ooh, my node went away, and I put that N in the wrong spot, so make sure you change it over to an A. So node, antinode, node, antinode. So I go up, I come down, and then I end up coming up here. I went up, I came down, and I ended here. So this length is 3/4 a wavelength, or in other words, lambda is 4L over 3. Putting in the other side of the oscillation envelope, and then looking at F equals V over lambda. So F equals 3V over 4L. Now if I compare this one and this one, we see that this new frequency, this new allowed oscillation frequency, is a factor of 3 bigger. So following our naming convention, since it is a factor of 3 bigger, we call this 3, and we can write it as 3F1. This is the next allowed harmonic, but again, following our our naming scheme, this would be the third harmonic. And then lastly, I add one more node antinode pair, so I now have 3 nodes and 3 antinodes. Up, down, down. So that follows from here, up, down, and I end here this time. Oop. Really did want that dot. So that's one full wavelength plus an additional fourth. So L equals 5/4 lambda. Or in other words, lambda is 4L over 5. Putting in the other side of the envelope and coming to F equals V over lambda. So that would be 5V over 4L, or in other words, 5F1. So this is the 5th harmonic. Okay. So we see in this case, when we have mismatched boundaries, a different behavior than when we had matched boundaries. First, the fundamental frequency is lower for the same length of string. For the matched boundaries, it was V over 2L. This one's V over 4L. And more importantly, we only have the odd harmonics allowed. The third one occurred, the fifth one occurred, but the second and the fourth didn't. So as I did on the last one, I'm going to summarize. So in this case, F1 is V over 4L. And I can write Fn equals NF1 again. But n in this case has to be an odd integer only. In the next unit, we are going to be applying our work on standing waves to looking at musical instruments.